All right, and so now in our final lecture, we just have one more thing to discuss. 10.4 is about areas and lengths in polar coordinates. Right then, so the idea is this. If you have a curve defined by some kind of polar function, like r equals f of theta, well, that's going to be a certain curve in the xy plane, and it might be a little weird looking. Let's just say we have a curve that looks like this. That could easily happen. You could easily get something like that from polar coordinates. Now, when we talk about area in polar coordinates, usually what we're talking about is we want to find the area of a region that's bounded by two rays. So like, suppose we have a ray like this, and a ray like this. And what we're wanting to find is the area of this region right here. Okay? So, if you want to do that, then, well, first of all, I just want to point out these two rays are defined by some angles, right? One of them is theta equals a thing, and the other one is theta equals a different thing. Let's call those numbers A and B. So let's say this one is theta equals A, and this one is theta equals B. So if you want to find the area of this region, you just have to take the integral from A to B of 1/2 r squared d theta. All right? So, let's see what we can do with this. Example. So we want to find the area of the region bounded by r equals cosine theta and the rays theta equals 0 and theta equals pi over 6. All right. Right, so if you wanted to graph a curve like this, well, we have r equals cosine theta. Depending on what theta is, r will be different, right? If theta in particular is 0, then r is 1. So theta is 0 along the positive x-axis, so at that point we're going to have a radius of 1, which we'll say is like right there. As theta increases towards 2 pi, r will decrease towards 0. So what we're going to get here is some kind of curve that looks kind of like this. Okay? At least that's what's happening between 0 and 2 pi. There's more, of course, but we're not interested in that part because we only need from 0 to pi over 6, actually. Okay? So theta equals 0 is just the positive x-axis. Theta equals pi over 6. Well, theta equals pi over 6 is kind of like this angle right here or so. So what we're trying to find here is the area of this weird looking region. So all we have to do is say the area is going to be the integral from 0 to pi over 6 of 1/2 r squared. In our case, r squared is just cosine squared theta d theta. Right then, so first of all, to be honest, I don't really know why I put the 1/2 inside the integral, because it's just a constant, which means you can always take it out. But for some reason, all books I've ever read do that, so I just did the same thing. It doesn't matter. You can easily take the 1/2 out. It's just a constant. So yeah, we'll do that. So we'll just say this is 1/2 integral from 0 to pi over 6 of cosine squared theta d theta. All right, now then, you need to now integrate cosine squared theta. The way to do that is you have to use the trigonometric identity. Cosine squared theta equals 1/2 1 plus the cosine of 2 theta. Okay? And then this just becomes 1/2 integral of 0 to pi over 6, 1/2 1 plus the cosine of 2 theta. And of course, then you have another factor of 1/2 that you can pull out. So this just becomes 1/4 integral from 0 to pi over 6 of 1 plus the cosine of 2 theta d theta. All right, so now we do this antiderivative. This becomes 1/4 times, okay, first term is just going to be theta because it's the antiderivative of 1. The other one, well, strictly speaking, I suppose we really need to do a u substitution here. We really need to say u equals 2 theta, and then du becomes 1/2 d theta. Put that in, and then take the antiderivative of 1/2 cosine u. But then you just get 1/2 sine u. And that's just the same thing as 1/2 sine of 2 theta. So this is just 1/2 sine 2 theta. And all of this is evaluated from 0 up to pi over 6. Right then, so this becomes 1/4 times, okay, theta is pi over 6, and then theta is 0. Add to this, okay, you distribute through the 1/4, you get 1/8. Sine of pi over 3 minus the sine of 0. 1/4 of pi over 6 is just pi over 24. And then the sine of pi over 3 is root 3 over 2. So this is just root 3 over 2 times 1 over 8. So that's root 3 over 16. And sine of 0 is just 0. So that's it. That's our area. All right, next up, let's look at a different polar curve. Same directions, but different curve and different rays to integrate between. So this one is 1 over theta. We're going to integrate this from pi over 2 up to 2 pi. Okay. Now, this one is weird. Because first of all, when theta is 0, that's not even defined, right? you know, like the theta increases as you go clockwise or counterclockwise around the origin. And then this thing is apparently decreasing. The radius is decreasing as theta increases. So what we're going to get here is a pretty weird graph. So as if theta is close to 0, then r is just arbitrarily large. But then as theta increases, r is going to get smaller and smaller. So what we're going to get here is a behavior that looks vaguely like a spiral, kind of like that. Okay. Now, all we're interested in is the region between pi over 2 and 2 pi. So, first of all, we need not consider the later behavior, really. All that we really care about is between pi over 2, which is right up here, and 2 pi, which is over here. So we're looking for the area of this region. So all we have to do is say the area is 1/2 integral from pi over 2 to 2 pi r squared d theta. And so in our case here, this is the antiderivative of 1 over theta squared just comes out to be negative 1 over theta. And you evaluate this from pi over 2 up to 2 pi. All right, so then this ends up being a 1/2 negative 1 over 2 pi minus negative 1 over pi over 2, so that's 1 over pi over 2. And then that's our answer. Of course, there's ways to simplify that, but not really important. Okay. All right, next up, let's find the area the area in the third quadrant enclosed by r equals 2 plus cosine theta. So we'll say and the third quadrant. Okay. This curve, r equals 2 cosine theta, is really weird looking. As you know, cosine always has to be between negative 1 and 1. So that means that r has to always be between 1 and 3. Like when r is, or when theta is 0, which is along the positive x-axis, we're talking about a distance from the origin of 3. Then when r is, or when theta is pi over 2, cosine is 0, in which case we're talking about a distance from the origin of 2. When theta is pi, this is 2 minus 1. So then we're talking about a distance of the origin of 1. When theta is 3 pi over 2, again, we get a distance of 2. And then when theta is 2 pi, we wrap around to where we started. Okay? It's a really weird shape that looks vaguely something like and that's not me trying to draw a circle, by the way. It's not a circle. It's really weird looking. There's an illustration in my lecture notes if you really want to see exactly what it looks like. Not that that's really important to solving the problem. All that we're concerned with is finding the region in the third quadrant that's bounded by this curve. So that would be this region right here. Now, that region right there can be understood as where theta is between pi and 3 pi over 2. So, the area is just going to be integral from pi to 3 pi over 2 of 1/2 r squared. In our case, r squared is going to be 2 plus the cosine of theta squared. So like this. Right then, so then this is integral from pi to 3 pi over 2. Okay, you have to distribute this now. So 2 times 2 is 4, multiplied by 1/2 you get 2. Then 2 times cosine theta plus 2 times cosine theta is 4 cosine theta, multiplied by 1/2 you get 2 cosine theta. And then finally, cosine theta times cosine theta is cosine squared theta. Multiplied by 1/2, you get 1/2 cosine squared theta. D theta. Okay? So now the rest of the problem just comes down to solving this integral. First of all, these two first terms can be handled fairly easily, I think. The antiderivative of 2 is just 2 theta. The antiderivative of 2 cosine theta is just 2 sine theta. This stuff is evaluated from pi up to 3 pi over 2. But then this next part is a bit tougher, right? We have to take the integral of 1/2 cosine squared theta. Well, if you remember, we did the same thing earlier today. All you have to do in that case is just to say cosine squared theta is 1/2 1 plus cosine of 2 theta. And then this becomes 1/4 integral from 0 to, no, it's not 0, pi to 3 pi over 2. 1 plus the cosine of 2 theta, d theta. Right then, so once again, this antiderivative just turns into, okay, we have 2 theta plus 2 sine theta, and then this new antiderivative is going to be 1/4 theta plus 1/4 1/2 cosine 2 theta, or 1/2 sine 2 theta. So that makes 1/8 sine 2 theta. All of this is evaluated from pi up to 3 pi over 2. All right, so first of all, I want to combine these two like terms just because it annoys me. 2 plus 1/4 is 9/4. So we have 9/4 theta evaluated from pi to 3 pi over 2. And we have 2 sine theta evaluated from pi to 3 pi over 2. And we have 1/8 sine 2 theta evaluated from pi to 3 pi over 2. Okay, so this first one just becomes 9/4 times 3 pi over 2 minus pi. This next one becomes 2 times, the sine of 3 pi over 2 is -1. The sine of pi is 0. Then we have plus 1/8. The sine of 3 pi is 0. The sine of 2 pi is also 0. So first of all, 3 pi over 2 minus pi is just pi over 2. So this becomes 9 pi over 8 minus 2. So So 9 pi over 8 minus 2, and that will be our area. Okay. All right, so now there's just one more thing to discuss, and that's the arc length of a polar curve. So, arc length is the same thing as it was before. It's just finding the length of the curve. Now, in my notes, I go through a little bit of how you get this formula, and I guess it's interesting. Basically, it talks about a connection between parametric descriptions and polar descriptions, but somehow I don't think it's really important for the lecture right now. So if you really want to see it, you can look through the lecture notes, but ultimately it just turns into this. The arc length is the integral from all right, so for some reason earlier today I said a to b for the bounds, but right now I'm saying alpha to beta, which is weirdly inconsistent because they're basically the same thing. They're both just rays determined by angles. So whatever, I'm just still gonna call this just a to b. Anyway, this ends up being square root of r squared plus dr d theta squared. D theta. All right. And as always, I feel like I need to say this again because it's the most common mistake I've seen calculus students making even this late in the semester. Once again, the square root of two terms added together is not the same as the sum of those two square roots. So we cannot write this as r plus dr d theta. That's not the same thing. Okay. So let's say find the length of the curve. This curve is r equals 5 to the theta for theta being between 0 and 2 pi. Okay, so this is another weird curve. It's going to be another spiral, but it's going to go the opposite way. Like instead of getting really, really close to the origin, it's going to get really, really far away from it. Okay? But in any case, if we want to find its length, we just need to use this formula. So we're going to need dr d theta. All right, so dr d theta, that's the derivative of 5 to the theta power, which, as you may or may not remember from Calculus 1, turns out to just be 5 to the theta times the natural log of 5. So in our case, the arc length is going to be the integral from 0 to 2 pi of the square root of r squared, which in our case is just 5 to the theta squared, plus dr d theta, which is just 5 to the theta ln 5 squared d theta. All right, so now you square these things. What we get here is integral from 0 to 2 pi of the square root of 5 to the 2 theta plus 5 to the 2 theta natural log 5 squared d theta. You can factor a 5 to the 2 theta out of both of those terms. So then this ends up being integral from 0 to 2 pi of the square root of 5 to the 2 theta times 1 plus natural log of 5 squared d theta. All right, now 5 to the 2 theta is being raised to the 1/2 power because it's under the square root. So then if you just multiply the exponents, you're just left with 5 to the theta. And that's actually completely valid here because 5 to the theta is positive over the region from 0 to 2 pi. In fact, it's positive everywhere. So yeah, we don't have to worry about any kind of absolute value shenanigans. So this just becomes integral from 0 to 2 pi of 5 to the theta square root of 1 plus natural log 5 squared d theta. Now, 1 plus the natural log of 5 squared, take the square root of that. That's weird looking, but whatever it is, it's a constant, so we can actually pull it out of the integral. So we can just write this as square root of 1 plus natural log of 5 squared times the integral from 0 to 2 pi of 5 to the theta d theta. All right, so now if you want the antiderivative of 5 to the theta, if you wanted the derivative, you just had to rewrite it and then multiply it by natural log 5. If you want the antiderivative, you have to rewrite it and then divide it by natural log 5. So this becomes square root of 1 plus natural log of 5 squared times 5 to the theta divided by natural log 5, evaluated from theta equals 0 up to theta equals 2 pi. And so you just go ahead and evaluate this. This becomes, well, I guess we can write it as square root of 1 plus natural log 5 squared divided by natural log 5 times 5 to the theta, or 5 to the 2 pi, minus 5 to the 0, which is 1. Whatever that number is, that's our arc length. All right, and let's just do one more example. Also about arc length. So this one is r equals 2 times 1 plus the cosine of theta. And theta goes from 0 to 2 pi. Okay. So this is another weird looking curve. That, you know what, all polar curves are weird looking. I'm just gonna say it. All polar curves are weird looking. And that's no exception. The point though is not exactly what it looks like, but just to find its arc length from 0 to 2 pi. So that's just what we'll do. The area is gonna be, no, not the area, what the hell am I doing? Arc length is going to be the integral from 0 to 2 pi of the square root of r squared, which in this case is going to be 4 times 1 plus cosine theta squared, plus, okay, then we need to square dr d theta, so of course we're going to need dr d theta, so let's see what that is. Dr d theta is just going to be negative 2 cosine theta, right? No, what the hell? Negative 2 sine theta. There we go. Okay. And so we square that and put that under the square root. So negative 2 sine theta squared. And then we take the integral of that. Okay, so then this becomes the integral from 0 to 2 pi of the square root of, okay, we'll just square this and distribute it. So 1 times 1 is 1, multiplied by 4, you get 4. 1 cosine theta plus 1 cosine theta is 2 cosine theta, multiplied by 4, and you get 8 cosine theta. Cosine theta times cosine theta is cosine squared theta, multiplied by 4, and you get 4 cosine squared theta. Then add to this 4 sine squared theta. And as always, in math, when you see cosine squared and sine squared happening together, you're going to look for a way to add them up and get 1. And we can do that here. Because if you just factor out the 4 from both of these terms, you just get 4 times cosine squared plus sine squared, which is 4 times 1. And then 4 plus 4 is just 8. So then this becomes integral from 0 to 2 pi of the square root of 8 plus the 8 cosine theta d theta. Right then, so then we have to take care of that integral. And then it's back to the weird factoring, because that thing just as it is, I think would be really hard. So what you have to do is figure out some way to turn this into a perfect square. Alright, well, let's see, how do you turn this into a perfect square? First of all, I suppose you could factor out an 8, and then you're dealing with 1 plus cosine theta, but then what's that? Well, 1 plus cosine theta that's the same as 1 plus the cosine of 2 1/2 theta, which in turn is the same as 2 times 1/2 1 plus cosine of 2 1/2 theta. And then based on our trigonometric identity, this part right here is just cosine squared of 1/2 theta. So this actually becomes 2 cosine squared 1/2 theta. Which is weird. Yeah, it's not every day that you have to use that backwards, but that's how it is today. Anyway, so we have 8 times 1 plus cosine theta, so that can just turn into 8 times 2 cosine squared 1/2 theta, which is just going to be integral from 0 to 2 pi, square root of 16 cosine squared 1/2 theta d theta. Now you can do the square root, and wait a second, I just realized something. Cosine of 1/2 theta I did take care of that in my notes. The way I did it is, I think, a little opaque though, so I'm going to expand on what I did there. So, here's the problem. Cosine of 1/2 theta is not positive from 0 to 2 pi. Right? Between 0 and pi, cosine theta is positive up until pi over 2, and then negative after that. So let's think about what we have to do here. First of all, square root of 16 is just 4, so this just becomes 4 integral from 0 to 2 pi, absolute value of cosine 1/2 theta. Yeah. We can't just cancel the square and the square root, because the truth is the square root of something squared is not always just that thing. It's only that thing if it's positive. If it's negative, then it's actually taking the absolute value. So in our case here, when we take the square root of cosine squared, that's actually the absolute value of cosine. Right, so now, what do we do with this? Well, we have to think about when cosine of 1/2 theta is positive, then the absolute value is just the original function and then fine. But when it's negative, now it's actually the negative of its own absolute value. So what we have to do here is we need to think about where cosine of 1/2 theta is positive and where it is negative. Okay, well, cosine of 1/2 theta is going to be positive between 0 and pi. And that's because cosine of theta is positive between 0 and pi over 2. It's going to be negative between pi and 2 pi, because cosine theta is negative between pi over 2 and pi. So what we have to do is we have to split this up along that breaking point. So this is for integral from 0 to pi of absolute value cosine of 1/2 theta, then integral from pi to 2 pi absolute value cosine 1/2 theta. So on the region where it's positive, we can just forget about these absolute value signs. There's absolutely nothing that the absolute value does to that, because it's already positive. When it's negative though, then the absolute value actually multiplies everything by -1 in order to cancel the negativity. And then you can pull that negative sign out, so then what you're actually getting is this. All right, so you do these antiderivatives. They're both going to be 2 times the sine of 1/2 theta, which when you multiply that by 4, you just get 8 sine of 1/2 theta. This is evaluated from 0 to pi. And over here we also get 8 sine of 1/2 theta. This is evaluated from pi to 2 pi. So 8 times sine of pi over 2 is 1. Sine of 0 is 0. Then over here we have 8 times sine of pi is 0. Sine of pi over 2 is 1. And then this turns out to be 16. Okay? Right, so the moral of the story here is just it's again just a formula that you need to plug stuff into. But just like for arc length of other kinds of curves, it's not always easy to do that. Okay? In any case, homework is up. Go ahead and get started on that. And this is the last time I will be saying that for this class.